For our last two examples, we're going to look at some more complicated types of problems. Here I have a definite integral from 0 to 1 of x minus 1 over x plus 1 dx. So I'm going to let my denominator equal x plus 1, and then my du is just x. So you see here that I don't have an expression in terms of u to substitute in for that x minus 1. So this is a problem where I have to solve my u, solve it for x, take my equation for u and solve it for x, so I get x equals u minus 1. And so x minus 1 is u minus 2. So I'm going to replace this x minus 1 with a u minus 2. Right. So that's the first step. Notice here also that since I'm taking this integral in terms of u, I have to change the limits as well. So right now the limits are in terms of x. I want them to be in terms of u, so I substitute those into my equation for u. So 0 plus 1 is 1, gives me my new lower limit, and 1 plus 1 is 2, that gives me my new upper limit. So I have this as my integral. I'm going to split that up. So I'm going to split it up into u over u minus 2 over u, and I get a nice easy integral like this. So here I have an easy, this is just going to be u, and here I have my du over u. So I'm still dealing with this definite integral. I have u minus 2 times ln of u evaluated from 1 to 2. I'm going to make the substitution. I'm going to substitute the 2 and substitute the 1 and subtract them. And now let's think about this for a second. I don't know what the numerical value of ln of 2 is, so that's okay. The ln of 1, though, is equal to 0. Natural log of 1 is 0. So this term here completely goes away, and so I have 2 minus 1 and then minus 2 natural log of 2. I can also bring this exponent to become the exponent of the 2 and the natural log, so that gives me ln of 4. So the 2 minus 1 gives me 1, minus ln of 2 squared is 4. Alright, the last example, what I want you to notice here is when we have an equation that is well suited for du over u, the kinds that we've been predominantly working on here in this set of examples, we have a higher exponent in the denominator than we do in the numerator. So in some of the examples I had like an x squared and then an x. So if I take the derivative of the denominator, I get something close to the numerator, and that's good for us. In this case, notice that it's a higher exponent in the numerator than it is in the denominator. And as a general rule, anytime that is the case, what I want you to do is divide these. So it's been probably a while since you talked about or thought about polynomial long division, but we're going to go over it again here. So we're going to do 2x cubed plus x divided by x squared plus 1. So I have that set up over here. So let's see how that works. So as I set up that numerator, I have a 2x cubed. I don't have any x squared term, so I'm going to leave a blank there, kind of a column, just sort of a space holder. And then I have plus x. And then I have my x squared plus 1 out here. So when I do this, I'm going to divide the leading terms. So I got a 2x cubed divided by x squared is going to be 2x. I'm going to line that up over my x column there. And then I'm going to multiply the 2x times the entire x squared plus 1. So 2x times x squared, 2x cubed. 2x times 1 is 2x. And then I'm going to subtract. So I have 2x cubed minus 2x cubed. Those cancel out. They should always, those leading terms should always go away. No x squared terms. And then x minus 2x is negative x. And so what I see here is that if I try to repeat that pattern, I go leading term divided by leading term, negative x divided by x squared. I can't divide that, so this is my remainder. And so that's where this expression here comes from. I have the answer I get by itself minus the remainder over the original denominator. And what I've done there is I have a nice simple integrand here that's easy to integrate, and now I have a du over u pattern. I have the exponent here is 1 higher than what's up here, so I'm going to let u equal x squared plus 1. When I take my du, I get 2x dx. It's really only x dx that I want to replace, so x dx is equal to 1/2 du. So I integrate, I find the antiderivative of 2x, I get x squared, and then using this u substitution, I get the problem in this form, and I have a nice du over u. So I have 1/2 natural log of the absolute value of u plus c, and then I put that x squared plus 1 in there. All right. At the end here, I could leave it that way. If I think about this, there's no way that x squared plus 1 could ever be a negative value. So I could write it also x squared minus 1/2 natural log of x squared plus 1 plus c. I really don't need the absolute value there, since that thing inside the parentheses is always going to be greater than or equal to 1 anyway.